Hello students, welcome to the lecture on UV visible spectroscopy. In the last lectures, I have discussed about electronic spectroscopy of metals or element and diatomic molecules. In this lecture, I will discuss about electronic spectroscopy of conjugated systems. I will also discuss about how your particle in a box concept, which we studied in quantum chemistry, will be applied to understand spectroscopy of conjugated system and spectroscopy of nanosystems. So, let us go ahead and discuss the electronic spectroscopy of conjugated system is generally known as UV visible spectroscopy. UV visible spectroscopy is quite often used in organic chemistry, physical chemistry and biochemistry. So, in UV visible spectroscopy, we deal with absorption of light in UV visible part of the spectrum, which is basically extends from 210 nanometer to 900 nanometer. As I discussed earlier, the transitions that results in the absorption of electromagnetic radiation in this region of the spectrum are basically transitions between electronic energy level, and generally we are concerned about the most probable transition, and the most probable transition is from highest occupied molecular orbital HOMO, lowest unoccupied molecular orbital LUMO. So, please change this to unoccupied. So, most probable transition is from HOMO to highest, HOMO means highest occupied molecular orbital, to LUMO, which is lowest unoccupied molecular orbital. In UV visible spectroscopy, we probe the various excited state of the system. So, here is your ground state and this is excited electronic state. So, we probe in this spectroscopy, we probe the various excited state of the system. Here light in UV visible region is used to promote your electrons from the one electronic level to another electronic level, one electronic level to other electronic level. Basically, we are going from ground electronic state to various excited electronic states. The particular frequency at which light is absorbed are affected by structure and environment of the chromophore. So, here we are going to discuss about conjugated double bond system as chromophore, and structure and environment of the chromophore will decide about the frequency of the transition, Your electrons in excited state can return to ground state by vibrational transitions through a small energy increment. So, they will first come to here and then it can also come back to your ground state. Absorbed energy appears ultimately as heat in solution. When the excited electrons returns to ground state by vibrational transition, in that case absorbed energy appears as heat in the solution. So, this is called non-radiative transition. This is known as non-radiative transition. I will also discuss the radiative transition from excited electronic state to ground state when I will discuss fluorescence. The type of electronic transitions are in organic molecule. Basically, we deal with sigma to sigma star, n to sigma star, n to pi star and pi to pi star transition. In inorganic transition metal complexes, we again come across electronic transition, and that is basically your DD transition, and in that DD transition will be governed by the manner in which 5d orbital splits on the nature of, or when ligand comes to metal, the 5 degenerate d orbitals of metal split into 2 different groups or 3 different groups depending on the nature of coordination. Nature of coordination can be of 3 types: octahedral, tetrahedral or square planar. Charge transfer transitions are also electronic transitions. They happen in UV-vis region, and it takes place in complexes in which there is a donor and acceptor group of electrons. I will discuss it later. Then we have electronic transition in conjugated system, and most significant transition is your pi to pi star transition. So, in this lecture I will focus on electronic transition in conjugated system. Some of them I have already discussed, few of them I will discuss after this lecture. So, if you go and look at the compounds, there are the few transition which happens in alkanes, and that is your sigma to sigma star transition. Common transition in carbonyl compound is sigma to pi star, and your pi to pi star happens in alkene, carbonyl compound, alkyne, etc. N to sigma star generally takes place in compounds containing oxygen, nitrogen, sulfur and halogen compounds, and your N to pi star transition takes place in carbonyl compounds. So, in carbonyl compounds there are 3 different kind of transition which can happen: sigma to pi star, pi to pi star and N to pi star, whereas alkene and alkyne have pi to pi star transition. And here is the different occupied level and unoccupied level. So, here sigma is the occupied level, pi, n, these are the occupied levels, and pi star and sigma star are unoccupied levels. So, you can see that when electron is in the n level and it goes to pi star, that is known as n to pi star transition. When electrons are in pi, outermost electrons are in the pi level, then it goes to pi star, it can go to pi star, and when it is in sigma, it can have sigma to pi star, it can have sigma to your sigma star. So, all these different kind of transition are possible. In this lecture, we will discuss mostly the effect of conjugation, particularly in alkene kind of system. The most significant transition is pi to pi star transition in alkene, and the value typically lies between 200 to 700 nanometer. We can actually calculate the value of lambda, and the way we do is by using the particle in a box kind of system. Using the particle in a box system, we can write the Schrodinger equation and we can solve to get the energy, of different electronic levels, and the delta E between two levels where transition is taking place will give you the value of lambda. And as I told you, that value of lambda lies between 200 to 700 nanometer. So, basically what you do is you take your molecule conjugated system as a particle and you confine between two walls, and then you can apply particle in a box approximation. So, molecules like butadiene, which is an alkene, can be treated as particle confined in one dimensional box. So, if you take butadiene, or you can think of hexatriene, these can be treated as particle confined in one dimensional box. And when we apply the Schrodinger equation for particle in one dimensional box, then we can get the energy of butadiene kind of system. Now, what is the effect of conjugation of alkene? If you go from ethylene to butadiene to hexatriene, and if you look at the energy, then the energy gap between HOMO to LUMO decreases. And so, the lambda of transition between HOMO to LUMO increases since energy gap decreases. So, it goes from 175 nanometer in ethylene to 258 nanometer in hexatriene. Now, we will like to see how we can explain this decrease in delta E and increase in your lambda value. So, for that we need to understand the concept of the particle in a box. So, let us first think of a classical case, a free particle in perfect one dimensional box. So, you are talking about big system, for example, racket ball, and now you are trying to see, or you are trying to look at its behavior in one dimensional box. So, one dimensional box is basically a space confined by two walls. Walls are infinitely thick, infinitely massive, and completely impenetrable. So, if you have this kind of system, then you are basically dealing with a perfect one dimensional box. Now, I told it is a free particle. What I mean by free particle, that no force acting on it. So, there is no force acting on it. When there is no force, it means potential energy is 0 here. Potential energy is 0, and since there is no way particle will be in this region or this region. So, in this region, let us say this is region 1 and this is region 3 and this is region 2. So, in region 1 and 3, your potential energy is infinite, because there is no way this free particle will exist in these regions. Okay. So, now let us think of the behavior of free particle here. So, suppose free particle here and I push it. So, it will rebound at this wall, it will go back, again it will come here, it will go back, and since there is no force acting on it, it will keep on doing this. It will keep on doing this, and since it is a free particle, so q is equal to 0, it means energy is equal to kinetic energy. So, energy will depend on velocity, energy will depend on velocity, and suppose if velocity is 0, it means kinetic energy is 0, and when it is 0, it will be somewhere on the surface line still. and so I know the position. It will be in between 0 and L, and if it is here, then it is at position x. So, I know the position of the particle. I also know momentum. Since I know velocity is 0 means momentum is 0 and the position is at x. And so, uncertainty in position is 0 and uncertainty in momentum is 0. So, this is for ball in perfect one dimensional racquetball court, where the length is 12 meter and mass of the ball is 0.04 kg. So, this is for ball in perfect one dimensional racquetball court. Now, let us think of the quantum case. In the quantum case, length is not 12 meter, length of the box is 1 nanometer, and particle has the mass of electron, which is very small, 9.1 into 10 to the power minus 31 kg rather than 0.04 kg. So, it must obey the uncertainty principle. It must obey the uncertainty principle. Here V cannot be 0. The particle cannot be standing at a specific point. Why V cannot be 0? If V is 0, then it will violate uncertainty principle, because you know V and you also know the position, which is simply not allowed by uncertainty principle. So, if V cannot be 0, which is velocity cannot be 0, then kinetic energy can also not be 0. Kinetic energy can also not be 0. So, one quantum racquetball can never stand still, and the energy of ball can never be 0. So, how to calculate the energy of a quantum particle in a box? So, if we simply allow the concept of, or simply take the concept of wave function, which is allowed due to quantum postulate, we may be able to get the energy of a quantum particle in a box without doing much calculation. So, what I mean by that is, please look at this picture. If you look at this wave function, this does not go to 0, am I right? And this wave function is not allowed, because if this function is allowed, then this wave function should go to 0 quite rapidly, or you can say that it will drop discontinuously to 0 outside the box. And so, this kind of wave functions are not allowed. If you remember, when I discussed about the postulates of quantum mechanics, I told you that wave function must be continuous, and here what you are seeing is that wave function is dropping discontinuously to 0 outside the box. So, what kind of wave function is allowed? The wave function is allowed which is 0 at the x is equal to 0 position and x is equal to L position. So, now you can think of how a wave function will look like in a box. So, wave function must be 0 at the walls, that is the very important criteria. Now, you see the first wave function you can think of, which is 0 at the wall, is when it starts from here, from 0 position, it goes back to 0 at this position. So, this is when n is equal to 1. Now, second thing will be, you start here, you go down to 0, you go back, you go like this, and it ends up at 0 at x is equal to L. This has to be like this because your light behaves as a wave. Now, the third thing which you can think of is first it decreases, goes up, becomes 0 here, goes up, then starts decreasing, goes to 0, goes to minima, and then again back to the phi is equal to 0. The phi is equal to 0, amplitude becomes 0. So, these are the allowed wave function, and if you look at the wave function, then what you will be able to get is lambda of the wave should be equal to 2 L divided by n. So, if n is equal to 1, then lambda is 2 L. So, you see here this is L is equal to lambda by 2 in this case. So, lambda is equal to 2 L. In this case L is equal to lambda, or lambda is equal to 2 L by 2. Here you can say 2 L by 1. Now, let us look at here, and this is L is equal to 3 lambda by 2. So, lambda will be 2 L by 3. So, for n is equal to 1 there is 1 here, for n is equal to 2 there is 2 here, and for n is equal to 3 there is 3 here. So, lambda is equal to 2 L by n, and again if you look at the wave function square versus x plot, it will look like this. So, now you have everything as positive, and the amplitude tells you about probability, phi square tells you about the probability. So, you can know what is the probability at the particular point in the one dimensional box, and these are the positions which are known as nodes. So, nodes are the points where the wave function crosses 0. Now, we know what is the value of lambda. Lambda is a function of n, which is known as principal quantum number. Now, let us calculate energy. We know that E is equal to half mv square, and using this let us calculate the momentum. So, p square will be p, we know that p is equal to m square v square. So, what I am trying to do is I am trying to relate E with p, and I know the relationship between p and lambda. So, I can calculate the energy as a function of n. So, energy is half mv square, and now I am trying to first express energy in terms of momentum. So, we know that p is equal to mv. So, p square is equal to m square v square. So, energy is p square by 2 l, and p is equal to h by lambda from de Broglie hypothesis. So, I am replacing p by h by lambda. When I plug in value of p to this equation, what we get is E is equal to h square by 2 m lambda square, and just I showed you that lambda is equal to 2 L by n, and so you can put it here, and what you get is E is equal to n square h square by 8 m L square, and this is the way you can know the value of energy of different electronic levels with n is equal to 1, 2, 3, 4. N can only take, if you look at the previous particle in a box, n can only take integer value. It can take 1, 2, 3. It cannot take a fraction value, because in that case the wave function will not be 0 at x is equal to L, x is equal to L. So, please keep that in mind, and here comes the concept of confinement. Concept of confinement, when a particle is confined in a one dimensional box, then its energy can only take discrete values. energy can only take discrete values. So, there is a discrete set of energy level for a given mass m and given box length L. N can take values 1, 2, 3, and so energy is h square by 8 ml square, 4 h square by 8 ml square, 9 h square by 8 ml square. This is when n is equal to 1, this will be when n is equal to 2, and this is n is equal to 3. As we know that the energy is given by n square h square by 8 m L square. So, if n is equal to 1, then you have h square by 8 ml square, and n is equal to 2, you have 4 h square by 8 ml square, and when n is equal to 3, then you have a 9 h square by 8 ml square. So, here your energy expressed in the unit of h square by 8 ml square. So, n is equal to 1, it means energy is 1 into h square by 8 ml square. So, n is equal to 2, then energy is 4 into h square divided by 8 ml square. So, now we know the energy of different levels. Now, we can discuss why our chair is red and blueberry is blue. This kind of question we will now be able to answer. So, let us discuss why a certain fruit color is red and certain fruit color is blue. So, we know now the energy of different levels E1, E2, E3, E3, and suppose the transition takes place between E1 to E2, E1 to E2. What does that mean is I am going from n is equal to 1 to n is equal to 2, and we know that E n is equal to n square h square by 8 ml square, and so E2 minus E1 will be equal to 4 h square by 8 ml square minus h square by 8 ml square. So, here n square is 4 when n is equal to 2, and n square is 1 when n is equal to 1. So, E2 minus E1 will be equal to 3 h square, 4 h square minus 1 h square, 3 h square by 8 ml square. Now, we know the value of h, which is this. We know the mass of electron, which is 9.1 into 10 to the power minus 31 kg, and suppose the length is 0.8 nanometer. Length of the molecule is 0.8 nanometer. Now, we want to calculate what will the value of delta E and corresponding lambda. So, delta E is 3 h square by 8 ml square. So, 3, this is h square to 8, this is mass of electron, and this is your length, which is 0.8 nanometer square, and this is for transition between n is equal to 1 to n is equal to 2. The delta will in this case will be 2.8 into 10 to the power minus 19 joule, and this energy corresponds to lambda is equal to 706 nanometer, which means that the fruit is going to have deep red color. Fruit is going to have deep red color. So, all these fruits have conjugated system or conjugated molecule, and when the fruit has conjugated molecule, we can take this molecule and consider it to be placed in a one dimensional box. In that way, we will be able to calculate energy of different electronic levels of that molecule. And once we know the energy, it is easy to calculate delta E and corresponding lambda. So, lambda for transition between n is equal to 1 to n is equal to 2 when the length is 0.8 nanometer. 0.8 nanometer is your 706 nanometer, which corresponds to deep red color. Now, you can think of same molecule, but with smaller length. For example, L is equal to 0.7 nanometer. In that case, your lambda will be equal to 540 nanometer, which will correspond to green color. And if L is equal to 0.6 nanometer, then it will have blue color. So, even for n is equal to 1 to n is equal to 2 transition, the color of a particular compound will be governed by its length, and if length is 0.8 nanometer, then it will correspond to deep red color. If L is equal to 0.7 nanometer, it will correspond to green color, and if L is equal to 0.6 nanometer, then it will correspond to blue color. Now, let us discuss particle in a box in a detail. So, first thing we need to write is Schrodinger equation. For that, we need to know what is the potential energy, and when we write Schrodinger equation and solve it, we will get wave function, we will get the allowed energies, and once we have allowed energy, then we can interpret the transition between different energy levels and lambda corresponding to those transitions. So, let us think about particle in one dimensional box. As we discussed, this space is confined by two infinite walls, and let us tell this space to be region 2, where your potential energy is equal to 0. There are two other regions, region 1, region 2. In this Vx is infinity, here Vx is equal to infinity. Again, since it is a free particle, so potential energy will be 0 in this region, and there is no scope to be for a particle to be in region 1 or region 3. So, Vx is equal to infinity. Now, let us write Schrodinger equation. This is time independent Schrodinger equation will be minus h cross by 2m d2 psi x by dx square. This is your kinetic energy term, this is potential energy term, and when we apply kinetic energy operator plus potential energy operator on the wave function, we will get energy as In value, energy at In value. So, now let us go and apply the boundary conditions. In region 1 and 3, this potential is infinity, and so wave function must be equal to 0. So, psi square must be 0. So, wave function must be 0 in these two regions. Now, let us go back and see what is the equation, this equation here and this. Suppose this V is 0, which is in this region, and so what equation is left is this is equal to E psi, and this basically gets a form like this: d2 phi x by dx square is equal to minus 2 m e divided by h cross square into phi x. The second derivative of a function equals a negative constant time the same function. So, this is basically a constant multiplied by phi. So, second derivative of a function equals a negative constant time this the same function. If you have this kind of differential equation, it is quite easy to guess what will be the solution. Now, let us think of this. The function with this property can be represented by sine or cosine function. So, function with this property is sine and cosine function. Function with this property is sine and cosine function. Now, let us think of if I take second differential, what will happen? So, let us take second differential of sin A x. We know that first differential is d by dx sin A x is equal to A cos A x, and when we take d by dx of A cos A x is equal to minus A square sin A x. So, that is what I have written here. And now, you can see that the second differential of this function is minus A square multiplied by same function. Similarly, you can do for cos A x by d square by dx of cos A x, and that will be minus A square cos A x. Similar way you can prove it. So, what does that mean is the solution of this differential equation is either sine function or cosine function. So, let us again go back to region 2 and try to solve this. So, minus h cross square by 2 m d2 psi x by dx square is equal to E psi, and if I take these 2 to this side, what I will get is minus d2 psi x by dx square is equal to 2 m in the numerator divided by h cross square into E psi, and then you get this differential equation, which is the second derivative is equal to, if you take minus this side, the second derivative is equal to minus k square psi, and for that your solution can be a sine wave function or cosine wave function, and general way to denote this is psi is equal to A sin k x plus B cos k x. Now, what we will do is we will try boundary condition, we will apply boundary condition to get the value of k. So, if I apply boundary condition, what we know that wave function is your 0 at the boundary. So, we know that at x is equal to 0, wave function is 0. So, if we apply that condition, so at x is equal to 0, wave function is 0. If I apply this condition, what I am going to get is b is equal to 0. Since sin 0 is 0, cos 0 is 1, and so b is equal to 0. So, now we got the value of b. Now, second condition is at x is equal to L, psi is equal to 0. So, at L also wave function must be 0, and if we apply that condition, what we are going to get is this 0 is equal to A sin k into L, and since A is not equal to 0, which means k L is equal to n pi, and thus the wave function is your A sin, in place of k you can put n pi by L. So, n pi x by L. This is your solution of the wave function, from the Schrodinger equation. But what is A? We have already calculated B, we know what is the value of k. Now, we need to know the value of A. Once we know that, everything is known, and you know what will be the wave function. So, for that you need to do normalization, and we know that in the normalization your psi star psi dx, when it should be integrated between 0 to L, it should be 1, because somewhere in between your particle is present. So, probability of finding the particle in the box is 1. Now, if you do this, what you are going to get is A square x by 2 minus sin 2 k x by 4 k and 0 to L. So, this is this part is basically integration of sin square k x dx, sin square k x dx. So, you do this integration, when you do this integration you will get this value. Now, you put these conditions, when you put this condition, what you are going to get is, when x is equal to L, then it will be L by 2 minus sin 2 kx. So, 2 k, put the value of k also, you will get this value, and for 0 you are going to get 0 here, and again here it will be 0. So, using this you will be able to get value of a, which is square root of 2 divided by L, which is square root of 2 divided by L. And thus, the normalized wave function for a particle in a box is equal to square root of 2 by L multiplied by sin n pi x by L, sin n pi x by L. Now, let us calculate energy levels. We know that k square is equal to 2 m E by h cross square. So, E is equal to k square h cross square by 2 m, where h cross is h by 2 pi, then E will be k square h square by 2 m into 4 pi square, and k we know k will be n pi by L. So, k square is n square pi square by L square multiplied by h square 2 m 4 pi square from here, and so energy is will be given by E is equal to n square h square by 8 m L square, and that is what we got when we applied this simple concept of wave becoming 0 at 2 volts. But now we have energy term, and as you can see it, E is dependent on n value, and n can take only value integer values. So, 1, 2, 3, 4, n can take values 1, 2, 3, 4, and once I know what is the energy level, now I can go and calculate what will be the value of energy of different levels of a conjugated system. So, this is your conjugated system, a double bond followed by a single bond, double bond followed by single bond. So, first thing is that what will the value of L? What will be the value of this L, or you can say that your size of one dimensional box. Generally, this bond is double bond is equal to 1.4 angstrom, and if you take in this direction, this length is equal to 1.2 angstrom. And so, you can know what is the length of this box. So, for example, if it is a 4 double bond system, now you see here 1.2, 1.2. So, this is your 2.4, this is 2.4, this is 2.4. So, this is 1.2. So, 1, 2, 3, 4, 5, 6, 7. And so, what you can do is you can write this as your 2n minus 1 multiplied by 1.2 angstrom. So, if there is a 4 number of double bond, then you have a 2 into 4 minus 1, that is 7 multiplied by 1.2 angstrom length. Now, each atom in the path of conjugation contribute 1 electron to the quantum energy level inside the box. So, how many atom is here? 1, 2, 3, 4, 5, 6, 7, 8, and each one of them is contributing 1 electron. So, total number of electron in the conjugated system is 8. From Pauli exclusion principle, only 2 electrons can occupy the same energy state. To have 2 same energy, they must have opposite spin, and a typical bond length in the path of conjugation is 1.4 angstrom. One thing you must keep in mind is this is larger than a bond length of carbon double bond carbon. It is not basically double bond character, since it is in conjugation with another double bond, and so it is between a single bond and double bond. Now, let us talk about the last system where there are 4 double bonds in conjugation. So, the number of electron in conjugation is 8, and so if I try to fill in the electronic states, the different molecular levels, how we are going to do is 2 is in this ground state, 2 is in this state, 2 is in this state, and 2 is this state. And this is your highest occupied molecular orbital, and this will be lowest unoccupied LUMO, lowest unoccupied molecular orbital, and this will be equal to p by 2, where p is total number of electrons, and so 8 by 2 is 4, and n is going to be 4 plus 1 5. Okay. So, this is your ground state of the molecule, and first excited state when 1 from HOMO goes to 1 electron from HOMO goes to LUMO, and now we can calculate delta E. So, delta E is equal to J square minus I square H square by 8 ml square. So, what I am giving is when I go from n is equal to I to n is equal to j, this will be the delta E for electron, and just we saw that j will be given by p by 2 plus 1, whereas I will be given by p divided by 2. If you remember that, in this case n is equal to p by 2 and this n will be equal to p by 2 plus 1. So, HOMO, for HOMO n is equal to p by 2, for LUMO your n is equal to p by 2 plus 1. So, I is HOMO and this is your p by 2, and j is LUMO, which is p by 2 plus 1, and 8 m p minus 1 into L square. Let me explain this here. We just calculated 2 n minus 1 multiplied by 1.2 angstrom, where n is number of bonds and 2 n will be number of electrons, okay, conjugated electron. So, p minus 1 into a small l will be equal to L, where a small l is 1.2 angstrom. And so, if I put it here, it will be p minus 1 into L square, and if you simplify it, what you are going to get is p plus 1 divided by p minus 1 square multiplied by h square by 8 ml square, and E photon will be equal to delta E electron, and so SC by lambda of photon will be equal to p plus 1 h square divided by p minus 1 square 8 ml square. Cancelling h on both sides gives you c by lambda is equal to this, and so you can know what is the value of lambda. Now, once you have this concept, now you can go ahead and calculate the lambda value for different fruits. Now, let me give 3 examples of fruits, for example, carrot, tomato and algae. Their color is due to different conjugated molecules. For example, in carrots there is beta carotene and its structure is given here. In tomatoes you have a lycopene and its structure is given here, and in algae there is equinone and here is the conjugation, and you can now see that there is a high degree of conjugation in this compound, and that basically results into color. Okay. Electrons, here electrons, you can think of electrons have wave property and they do not jump off the pigment when they reach its end. The electron resonances determines which frequency of light and thus which color are absorbed or emitted from the pigment. So, it is not very difficult to calculate that. I have already told you that if there is p electron in conjugation, then this is the formula which can be used to calculate the value of lambda. And same thing you can do it here. You see here conjugation 2, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20 and 22. These are the number of electrons in conjugation, and now you know the value of p, you can calculate what will be the lambda. Now, can we calculate the lambda value of for cyclic conjugated molecules, because there are lot of molecules in the nature which is a cyclic conjugated molecule. For example, your chlorophyll or protoporphyrin, they have a cyclic structure and they are cyclic conjugated system. Here again we can apply the crude quantum model. Now, you can think of this as a ring, and for ring the resonance condition is 2 pi r is equal to n lambda. If you remember, we have discussed this when we were discussing rotation. So, the resonance condition is 2 pi r is equal to n lambda. So, now I know the lambda value, and since lambda is related to momentum p, and so I can know what is the value of p, and now p is related to energy, and so energy can be calculated. So, 2 pi r is equal to n lambda, and we know that p is equal to h by lambda, and so your p will be n h by 2 pi r. So, you can simply put h by lambda will be equal to 2 pi r, and that is all. And now, once we know the value of p, we can calculate energy of the electron, and that will be given by p a square by 2 m. So, p is equal to n h by 2 pi r. So, take a square of this and divide by 2 m, you can get the energy of the electron. And now, you can see energy is once again quantized, because n can only take value 1, 2, 3. So, it depends on variable n, which possesses discrete value, and so we have only discrete energy levels. Time is up. So, I will discuss about this electronic material thing in the next lecture. Thank you very much for listening. I will directly go to acknowledgement section, and I will recommend you to read the book called Absolutely Small by Michael D. Fair, very well written book. And certainly you can also look at Banwell book and the book written by me. Lot of figures has been taken from these books or waves, and I have tried to acknowledge all of them.